So I don't know if you used to do this, but when I was a kid, I used to go down to a lake, ocean, whatever it is, find a really big rock underwater, and I'd be able to lift up the rock when it was underwater. Of course, that huge rock, if it was not underwater, if it was on the beach, I'd have no chance of lifting it. So I'd like to feel, really strong, lift this huge boulder underwater. But why was that possible? So here's my rock under the water, and what's happening here is that I have the force of gravity pulling the rock down. We always have that. But underwater, there's an additional force called the buoyant force that is from the fluid surrounding the object. So anytime I have an object surrounded by a fluid, there's going to be this buoyant force caused by that fluid around it. Question now is, where does that actually come from? So if you remember from a couple lessons ago, hydrostatic pressure, anytime I'm in some certain depth of fluid, I'm going to have a pressure caused by the weight of the fluid above it. So if I look at the pressure on top of this rock, I have some pressure associated with this distance d, the depth of my rock. If I look at the bottom of my rock, it's down a further distance. So d plus h is my total distance. That's going to give me a higher pressure on the bottom. So that's why I have bigger arrows on the bottom than the top. So this difference in pressure, higher pressure on the bottom, lower pressure on the top, that gives me a net force in the upwards direction. That net force in the upwards direction is exactly this force, Fb, the buoyant force. So as I just said, difference in pressures gives me that net force in the upwards direction. So what I want to do now is derive the equation for buoyant force. As I said, this comes from the hydrostatic pressure difference from top and bottom. So fluid here has some density rho, object has some height h, cross-sectional area, so perpendicular to h, has some area a, and then I have the topmost surface at some depth d. So as I said, based on that, I'm going to have some pressure pushing down on the top. That pressure pushing down on the top is from the hydrostatic pressure in the fluid, rho g depth. So in this case, my depth of my top surface is d, so rho g d on my top surface, that's pushing down. And then on the bottom surface, I have a pressure pushing upwards. Again, hydrostatic pressure, rho g times the depth. In this case, the depth is d plus h. So with those two pressures, I can turn those two pressures, both of them, into forces just by simply multiplying by the area. Doing this, I'm assuming that my pressure is constant along the top surface and on the bottom surface. Even if it's not, if I have some weird shape like I have here, all I need to do is integrate the different pressures over the area. You end up with the same answer, it's just a lot harder math, so do it the easy way. So I take my forces, I want to find the net force. So my net force is the bottom pushing up minus the top pushing down. So total force is the bottom minus the top. Bottom, I have this pressure, rho g d plus h. To make it a force, multiply by area. Top, rho g d, multiply by area. Then expanding this out, I have rho g dA minus rho g dA. Those guys cancel out. All I'm left with is rho g h times A as my net force pushing upwards. So if I take that net force, rho g h times A, because I have a cross-sectional area A, height h, h times A is simply the volume of this object. So another way to write that is that F net is rho gV. And then this net force caused by this pressure difference is exactly what this buoyant force is. So essentially my buoyant force, rho g times V, is the equation for that. And then note that density times volume is actually a mass. So density times volume is actually a mass. So my buoyant force is actually m times g, that's a weight. Remember, this density is the density of the fluid, so the buoyant force is equal to the weight that would be here if the object wasn't. So this leads to another description of the buoyant force, which actually comes from about 2,000 years ago. Archimedes' principle, which says that an immersed body is buoyed up by a force that's equal to the weight of the fluid displaced. So again, my buoyant force was equal to the weight, but it's the weight of the fluid. So if I had this object, whatever the weight of the fluid that was there before this object was here, that's equal to this buoyant force. So that's another way to calculate it. So you can see what this means for my object. If my buoyant force is bigger than the force of gravity, this object's going to move upwards, start to float. If my buoyant force is less than the force of gravity, it's going to move down, it's going to sink. If they're both the same, then it's going to just sit here, not do anything, net force is 0. So a quick question, while you think about this one, have a boulder, throw it into a deep lake. As it sinks further and further down in the lake, does the buoyant force get bigger or smaller? So think about that for a minute. And the answer actually is neither. It actually stays the same. Assuming there's no density changes, nothing weird is happening. So think about this, as my rock gets further and further down, this distance d gets bigger and bigger, which means I have a higher pressure, but I have a higher pressure on the top and the bottom, and my hydrostatic pressure, buoyant force, comes from the difference of the two hydrostatic pressures. And so even though this guy's getting bigger, this guy's also getting bigger, they're getting bigger by the same amount, so when I subtract them, they end up canceling out. All I'm left with is the h, just like I had before, and so same buoyant force either way. So time for a couple examples. First example, easy one. I have a 1 liter container completely filled with lead. That's going to have a mass of 11.3 kilograms. Then put it in some water, and I want to know what the buoyant force is then acting on that container of lead. So when I throw that 1 liter container of lead into water, it's going to displace 1 liter of water. So that's my volume, 1 liter, or 0.001 cubic meters of water. And so then my buoyant force, density of water, volume displaced times gravity. So density of water, 1,000 kilograms per cubic meter. My volume, 0.001 cubic meters. And then gravity, of course, 9.81 meters per second squared. Gives me a buoyant force of 9.81 newtons in that case. So next, slightly harder example. I have a flat bottom barge loaded with coal. Total mass of 300,000 kilograms. So that's the barge and the coal total mass. Barge is 20 meters long, 10 meters wide, and I want to know how far does it drop down in fresh water. So you have this barge going up a river or something. You want to know how deep you are because you don't want to run aground. So I want to know what the depth is based on the scenario. So to solve this, first thing I want to do is look at Newton's second law in the vertical direction. So I have two forces, gravity pulling down my barge, buoyant force, water pushing it back up. So in terms of Newton's second law, I have force in the y direction, Fb pushing up positive, Fg pushing down negative. Those guys equal mass times acceleration, but because this barge is floating, it's not moving up or down. So if it's not moving up or down, acceleration 0. So what this turns into is that Fb, my buoyant force, equals Fg, the weight of the boat. So buoyant force, we know, is density times volume times gravity, density of the fluid, volume underneath the water, and then weight, simply m times g. G's cancel out. I'm left with density times volume. Volume is the area, the bottom area, times this depth. That's the volume underwater. That's the volume displaced, so that's the volume I want to use. And then equals the mass. Rearrange this. I can find the depth is mass divided by density of water times that area. So mass of 300,000 kilograms, density of fresh water 1,000, and then my area 20 meters by 10 meters gives me a depth of 1.5 meters. So hopefully the river is at least 1.5 meters deep the entire way. Otherwise I'm in trouble. Alright, so third and final example for this lesson, you have a hot air balloon. With that hot air balloon, you want to lift a basket load of 600 pounds. So basket and everything inside it weighs 600 pounds. Ambient temperature 59 degrees Fahrenheit. So in those conditions, how hot must the air inside the balloon be to actually get this thing off the ground? So again here, solution starts by using Newton's second law. I have all my forces in the vertical direction. Buoyant force pushing me up, which is why I'm going to get off the ground. This basket load, 600 pounds, pulling me back down. And something you may not have thought of is I also need to get all the air inside that balloon up as well. So I have a whole lot of air inside my balloon that also needs to be lifted. So that is also a weight that this buoyant force needs to overcome to get this whole thing off the ground. And that, just to achieve liftoff, needs to be equal to 0. Technically, this buoyant force has to be a little bit bigger than that, but equals 0 is close enough. So essentially my buoyant force is the two weights, load, and the hot air. Buoyant force is density of the fluid around it, so this is the ambient air. So rho A is for the air around it, 59 degrees Fahrenheit. Volume of my balloon, and G, volume of balloon, is what's being displaced. So I'll have my 600 pound load. And then in terms of the weight of the hot air, that's the mass of the hot air times gravity. Mass of the hot air is density times volume. So rho H for the hot air times, again, that same volume and gravity. Rearranging this, I'm solving for the density of the hot air, because using the ideal gas law, I can translate the density into a temperature. So what I want to solve for here is the density of hot air. So solving for that guy, moving him over, moving the ambient air, moving the load to the other side, then dividing by V and G. Density of hot air is the density of the ambient air minus the 600 pound weight divided by volume and gravity. Volume for a sphere is pi d cubed over 6. So I'm going to replace this with pi d cubed over 6. Gives me a 6 on the top, pi d cubed on the bottom. So there's my equation for the density of hot air. Ambient air, 6 times that 600 pounds divided by pi d cubed over g. So with my equation up here for my hot air density, I don't know the ambient air density, so I define that first. But everything else I know. I know my load, 600 pounds, know the diameter, and know g. So first thing I need to do is find the density of the ambient air, so ideal gas law, pressure over RT. Assuming standard conditions, 14.7 psi. Of course, I want that in terms of PSF, not PSI. So 14.7 multiplied by 144 square inches per square foot gives me that in the proper units. And then R value in these units, 1,117 pounds feet per slug degree ranking. Then my temperature, 460 plus 59 degrees Fahrenheit, puts that into ranking degrees, again, absolute temperature there. Gives me a air density of 0.00238 slugs per cubic feet for the ambient air. And now I can plug that in to find my hot air density. So there's my ambient air density minus 6 times my 600 pound weight, pi, 50 feet diameter cubed, and gravity, 32.2 feet per second squared. Brings me a hot air density of 0.00209 slugs per cubic feet. So that's the air density that I need inside my balloon. The question, of course, wanted the temperature. So to find the temperature, again, ideal gas law, find the temperature, pressure over density, and R. So pressure, again, 14.7, 144 for the right units. This density of 0.00209 slugs per cubic feet. Then, of course, same R value, 1716, gives me a temperature of 591 degrees Rankine, which is 131 degrees Fahrenheit. So that's the temperature that I need inside my balloon to get this off the ground.